Hey everybody, this is Mr. Grabo. We are going to go over the second part of the notes, so fill in the blanks and make sure that you listen to the whole presentation so you understand what's going on. Don't just fill in the blanks, but actually listen to the presentation, okay? All right, so we got small grains of dust and rock that are about, say, 3 feet in diameter or smaller. Those are going to accumulate and get larger, and as they grow and grow and grow, they become what we call a planetesimal. Okay, a planetesimal is just a rock that's up to about a half a mile in diameter, and we call this process of this building of the rock getting bigger and bigger and bigger, we call that planetary accretion. It's the accretion of material that builds up a planet. So these planetesimals, these smaller chunks of rock, they're going to accumulate, they're going to get bigger and larger, and eventually they become self-gravitating bodies that we call protoplanets. So they're a few hundred miles in diameter. So it's just a larger chunk of rock with a lot more gravity. These protoplanets will eventually form into full-size planets. They're going to collect all the material around it, and it's just going to collect and get bigger and bigger, similar to the Play-Doh activity that we did where we rolled the spheres around and they will eventually become one big giant ball of Play-Doh. In this case, it's creating a planet. Okay, so on the right side, this is kind of the progression of the planet formation. So you want to fill in on the right side using the words planetesimals, protoplanets, and then finally planets. And we can see here, I'm going to give you the answer. We got planetesimals, are smaller chunks of rock. They become protoplanets, and then eventually they become planets. Okay, so another thing that's happening here is we have what's called the frost line. Okay, so elements and compounds, they are going to condense, meaning they come together and they solidify during this period based on their two things, their temperature and how heavy the elements are. So rocks and minerals condense closer to the sun because they're more massive, they're heavier. Things like copper and gold and iron rocks, they're going to be more massive, they're just a heavier density. And so they're going to condense at higher temperatures. Okay, these things are real easy to condense. They don't take a real cold temperature. But now things like hydrogen compounds like methane and ammonia are going to condense farther away from the sun at much lower temperatures. It takes a lower temperature for them to become a solid, to cool down those molecules and become an actual solid. So their masses are lower, things like nitrogen and hydrogen compounds, just they're much smaller molecules than metals, and so it takes a lower temperature to get them to condense and turn into a solid. Okay, so this boundary line between the two is what we call the frost line, and it's right in between Mars and Jupiter. So on the right side of your paper, I want you to draw and label where the frost line would be. And I'm just going to scoot over here to my notability, and we can see, so inside of here, it's much warmer inside of here, and this is where we get rocks and minerals condensing. Outside of that frost line, it's much cooler, and this is where we get the hydrogen compounds like ammonia and methane, and those things will condense and turn into solids outside of that frost line. Okay, so right in between Mars and Jupiter, right where that asteroid belt is, that's where our frost line is. Okay, so on the inside of that frost line is where we get the terrestrial planets. So these planetesimals and protoplanets closest to the sun are going to be made up of mostly rock and metal. These protoplanets are going through accretion, they're getting larger and larger, and they build up into terrestrial or rocky planets. So this type of planet is going to have a metallic core. It's going to be made of metals like iron. It's going to have rocky mantles and rocky crusts. Okay, and as you can see in the picture here, we can see, I'm just going to use Earth as an example. We have a solid inner core that's made up of iron, and then we have a solid rocky crust on the outside of the Earth. So we kind of have that core and mantle and crust on these rocky planets. Okay, so the rocky planets or terrestrial planets would be Mercury, Venus, Earth, and Mars. Those are the inner planets, and they're the terrestrial planets. Okay, the gas planets, we call those the Jovian planets or the gas planets. They're made up of hydrogen compounds and ices, things like ammonia and methane. And these condense outside of that frost line because it's much colder way out past that frost line where it's much colder farther away from the sun. Okay, so as these things condense, they're going to capture hydrogen gases and helium gases, and they become larger and larger, similar to how the rocky planets do, only these are going to be made up of gases. So Jupiter, Saturn, Uranus, and Neptune are all part of those gassy planets. Okay, so on the right side of your paper, go back to the solar system picture and give 2 details about the planets inside and outside the frost line. So make sure you go and do that. I'm not going to do that for you. You can pause the video and go do that. Okay, the next thing is about the formation of the moon. You can see in this animation here, there's a large object that's colliding with the Earth and is causing the inside of the Earth to get smashed out into space. All of that rock and part of the mantle is going to get splashed out into space. So it's a Mars-sized object that's hitting the Earth, and this is what we think happened to create the moon. So this leading theory suggests that a Mars-sized object hit the Earth, and that debris, it literally splashed part of the Earth out into space, and it will eventually form into the moon. So the rocks from the Earth's outer crust would have been thrown into orbit around the planet after a catastrophic impact on the early Earth. Okay, here's another animation where you can see that. So we can see a large object is hitting the Earth, splashes a bunch of the Earth's crust and mantle out into space, and it eventually will coalesce into what is now the moon. Okay, so this material would have formed a ring, kind of like Saturn's ring, but it's going to be more rocky and less ice. It'll eventually accrete, come together. Those little chunks are going to combine due to the force of gravity and become what we know as the moon. So I'm going to show you a little clip here.
Theory with which most people agree, which is that it was made in an impact. So very early on in the life of the solar system, so let's say 4.5 billion years ago or so, we think that a planet about the size of Mars collided with the young Earth. It's a glancing blow, actually, which caused a lot of rubble to go out into space, formed momentarily a ring around the Earth, somewhat like the rings around Saturn, but then that ring very quickly coalesced into the moon. So we think that the moon is made of mainly bits of the Earth and also bits of this other planet that glanced off it 4.5 billion years ago. It's very, very early, very soon after the Earth formed. There is a theory that...
Okay. So the next thing I want to talk about is what's called the heavy bombardment period. So the final stage in Earth's formation history is known as the heavy bombardment period. So this is a time of increased meteorite impacts on the planets and the moons. It's just things are shooting all over the place, and the Earth is just getting clobbered by all these meteorites, things that are floating around, all these spare pieces of rocks that are flying around. They're constantly in collisions with the different planets and the moons. So the Earth would have just been hit over and over and over by these meteorites, including the moon. So the evidence of this time period can be found by looking at the craters on the moon. We notice that there's tons of craters on the moon, but we don't see that on the Earth. We can see it on the moon, though. So this is also one of the ways that people theorize where the water could have come from. Some water, ice on these meteorites hit the Earth, and the Earth just accumulated this water. Maybe comet type of impacts as well that could have led to the accumulation of all the water that we now see on Earth. So on the right side of your paper, why do we not see craters on the Earth from the heavy bombardment period? We can see it on the moon, but we don't see it on the planet Earth. So think about that for a second. Why would we see evidence of that on the moon, but not on the planet Earth? Okay, next time we're going to jump into the evidence that supports these ideas. If you have any questions, you can reach out to me, and I will see you on Monday.